Let's go ahead and start our strict capital budgeting example. What I've done here is I've created 5 assets, A through E. And I've shown you the restricted component that we have, which is their cost in the year that you're supposed to purchase them. Now remember, the assumptions for the strict capital budgeting are that you have restrictions on first year cash flow. There's a limitation there, but not any year that comes after. To do anything more complicated than that is a little beyond the scope of this course. You end up with kinds of constrained optimization problems that we just can't cope with. I've also associated with each one of these assets a present worth. Now, it doesn't matter which interest rate we use in order to calculate that present worth. It's done for you. You can safely think of it as 10%. So what we've done here is we have asset A, which is cheap to get into, costs only $2, gives you a present worth of 2. Asset B costs you 7, has a present worth of 3. Asset C costs you 10, has a present worth of 7, and so on down the line. Now the first thing you'll notice is asset E costs you $20 but has a present worth of -1. What I should point out is that this is never an asset that you're actually going to try to use. It's something that you would eliminate from any possible combination. You know it won't be part of your winning combo. Now, what you're doing in order to find out the best choice for a capital budgeting problem is you're taking all these asset combinations and seeing which combinations fit within your capital budget. Now, what I'm actually doing here is I'm saying in this problem we'll have a capital budget of $20. So the idea is that in time period 0, you can buy as much as $20 worth of stuff. So there's a limitation not on how many assets you can buy, but what you can fit into your $20. Now to make this clear, you can buy all those little singletons there, so it makes sense to buy asset A by itself, asset B by itself, asset C by itself, asset D on itself. Each of those fits under the $20 heading. But you can also buy combinations. So for example, asset A and B together cost you only 9, so you can definitely buy that. Asset A and C together cost you only 12, you can buy that. Asset A and D cost you 17, so you can buy that. B and C cost you 17. B and C cost you 17, you can buy that. B and D, on the other hand, cost you 22. That's a combination that you can't quite get to. You can eliminate that. And so what I'm doing here is I'm looking at the combinations which are actually feasible that you can fit in that $20 budget. Please note C and D is also something that can be knocked out of that feasibility set. Now there are also some three-way combinations in there too that are possible. And again, we're looking at all combinations you can fit in the $20 set. So that ABC combination costs you 10 plus 7 plus 2, 19, definitely feasible. But the A, B, D combination that's just below that, too expensive, can't afford it. That B, C, D combination, also can't afford it. In fact, all of these other three-way combinations and four-way combinations are not things that you can afford. And so what I've done here is I've blocked out everything that you either don't want to get because that is a negative present worth, or things that you can't afford. Now what we're trying to do here is find the combination that gets you the maximum present worth. And so you can scan down on these that are still feasible and notice that this ABC combination gets you $12 worth of present worth. Now what's interesting about this ABC combination is if you add up these values, how much you spent, the 10, the 7, and the 2, you find out that you didn't spend all the money. Now for capital budgeting problems, this is actually quite common because that internal rate of return that you calculate isn't exactly the opportunity cost, because your opportunity cost includes these foregone other options. Part of the opportunity cost is, say, you giving up investing in asset D. So it's very common to have a relatively small amount of money left over, and it's also relatively common to have some asset that has a high internal rate of return that gets left out for whatever reason. Now, this kind of combinatorial optimization problem is done all the time. If you want an interesting example of it, you can take a look at the Multnomah County budgeting process. What they do is they have these program offerings. Each one of them has a certain amount of cost, and you have benefits that are measured in some way. And what happens is they try to gather together the right combination of these investments in order to maximize the benefits that are available. And you can also, by watching the Multnomah County budgeting process, see how to best react to what happens when your small, high-value project, in terms of internal rate of return, doesn't get funded because it gets pushed out by other assets. And the best thing to do is not argue that your investment is better than somebody else's investment. That tends not to work. What you do is you argue to expand the amount of money that's being spent. And that's actually what you see when you see people fighting over budgets in Multnomah County. They're always talking about adding in some contingency funds or adding in some one-time funds in order to fund more projects. So you're not trying to go head-to-head with other projects. What you're trying to do is make it so that the funds available are somewhat larger. And the final thing I want to warn you about with these optimization problems is that you get past about 5 assets and suddenly this becomes something which is really, really, really difficult to do. You're required to have a computer in order to handle all these combinations, and after a certain point, computers can't handle it. You may have something like an inventory list, not an inventory list, but a maintenance list that has 100 items on it. And trying to find the best combination of 100 items to fit within a capital budget can be extremely difficult. In fact, the number of combinations within that exceeds the number of elementary particles in the universe. It's not something you can just throw more computing power and find the best solution. The best you can usually hope for is something which is approximately correct. And finally, these solutions are all predicated on you being able to take that remaining funds and actually throw it into a minimum acceptable rate of return and receive benefit from it. If you're in a situation where if you're given a capital budget and you don't use it and you actually lose it, again, that minimum acceptable rate of return doesn't show the opportunity costs. And in fact, in those kinds of situations, it's quite common for people to actually just spend their entire capital budget desperately finding something which will provide some benefit for the money, not necessarily maximizing the benefit, taking into account that there is this opportunity cost, the minimum acceptable rate of return.